Hello and welcome to lesson number 32, the birth of quantum mechanics. Now, I know as soon as people hear the words quantum mechanics, they can get nervous that this is going to be like a really difficult chapter to get through and it's going to be hard to understand. What I will say is this. A lot of the terminology, a lot of the ways that we talk about quantum mechanics, that's going to be where you have to be most careful. Because even though you might not use terms like velocity and displacement in everyday language, we have a pretty good idea of what they mean. But when I get into talking about things like work functions and threshold frequencies, that's where things kind of separate out. So what I'd really strongly recommend you do is kind of make almost like a glossary for yourself of terms throughout the quantum mechanics chapter and just try to stay on top of the language that way. But also, maybe more so than other chapters, make sure that you're doing homework from this chapter. Even if you might kind of go a little light on that some of the time, you've really got to be working through problems, and that's how you're going to make the language of quantum mechanics start to kind of click in place with you. So to start off, what we end up doing is looking at basically physics up until the end of the 1800s. Really, we're going to find it's exactly up to the year 1900 itself. Physicists could look back at about 300 years of incredible progress. When you think of all the things you've already studied across Physics 20 and Physics 30, there's a lot of material. And we've very successfully explained a lot of things, whether it's Newton and his laws, Maxwell bringing together electricity and magnetism, Thomson figuring out mass of subatomic particles. This is all awesome stuff, and there's so much more that was done. So physicists had this attitude at the end of the 1800s that it's only a matter of time for us to come up with the last few answers to some nagging questions, and then physics would be effectively finished. Like, we'd have a complete story of the universe. Now, I hope you can look at that now and realize that anytime somebody in the field of science would have that sort of an attitude, they are really, really wrong. Because every time we ask a new question and we come up with an answer to it, those answers usually lead to other questions that we need to answer. But, you can even look at somebody like the quote there I've got from Michelson, a person who's extremely well respected in the history of physics, where he agrees with this idea that the only thing that's going to happen is we're going to get more precise answers. It's almost like talking about him measuring the speed of light. Oh, we'll just get better at measuring it to more decimal places, but we're never going to learn anything new. Now, one of those ideas that they were having problems with is something that was called black body radiation. And I also like that when I was learning about this years ago, we also referred to it as cavity radiation. And I want you to keep that kind of in mind while I'm describing this object to you. I tell you that it's made of black body material. And what that means to us is that it perfectly absorbs any wavelength of any form of EMR that strikes it. Visible, gamma, UV, radio waves, whatever. If any type of EMR touches this, it gets perfectly absorbed. And you have to understand just how uncommon that would be, because when we think about objects in our day-to-day life, we think of most of them as having colors that we can see. That means they're reflecting some colors of visible light. But even objects that appear black to us, other forms of radiation can hit them and be reflected off. So this idea that something could absorb all forms of EMR is kind of a wacky one. And the picture that I've got for you here is to imagine that black body as having a hole drilled in it so that we actually shoot some EMR into it. And I'm kind of depicting it here as visible light stuff, but it could be any form of EMR. And that all of that EMR going into that hole that I've drilled into the black body object would be perfectly absorbed. And here's the part that sometimes people forget. It would also be perfectly re-emitted with absolutely no loss of energy whatsoever. So it perfectly absorbs and perfectly re-emits. Now, you might say, well, if this is so uncommon to our day-to-day experience, why even bother talking about it? Is this just some theoretical idea, and why are they getting so hung up on it? Well, actually, black bodies, in a sense, are about the most common thing that you can see in the universe. Because stars, even our sun, essentially act as black body objects. The light, even the visible light that we see coming off of our sun, was actually created, released tens, if not hundreds of thousands of years ago, deeper in closer to the core of the sun where the actual fusion process is happening. And it's taken that long for it to reach the surface and come out to us through space and here to Earth. Going through all the material that makes up the sun has taken thousands upon thousands of years, where that EMR is constantly bumping into particles of star material and then re-emitting and absorbing and emitting over and over and over again until it finally makes its way to the surface. And then it takes about 7 minutes for it to reach us here on Earth. But that means that if stars essentially act like black body objects, we better understand black body radiation very well, because that means that we have an explanation of stars. So, if you're going to go with a classical physics, and I mean before the year 1900 explanation of this, the idea would be that as higher and higher frequencies of incident EMR, the incoming EMR, would hit a black body object, it would excite the particles of the black body object up to higher and higher energies, and we would expect that the intensity of the emitted EMR coming off of it should be greater. More energy means faster vibrations, means higher frequencies. So, when physicists thought of this in the most classic of ways, they would graph it out like this. They would say at low frequencies we got low intensities of EMR being released, but if we go to higher frequencies of incident EMR, the intensity of the EMR emitted by the black body should be greater. Well, small problem. This is not the way it works. When they actually looked at basically our sun as a model of a black body object, what they found is that instead of following that classical theory prediction, the actual real world does something like that curve. Sure, for the first little bit at lower frequencies, it actually does pretty much match the classical theory. You get pretty much as the frequency is increasing, the intensity increases. But then you reach a point where at a certain frequency, it starts to drop off. And then it really drops off. So that even though we're going to higher and higher frequencies, the intensity of the EMR is actually decreasing. That goes against the way that classical physics would explain any of this. So, physicists tried to figure this out. And this was, like right at the very end of the 1800s, them trying to figure it out. Physicists with names like Wien, Rayleigh, and Jeans. These are some of the biggest physicists that lived in the late 1800s. And they are the way that we today think of people with names like Stephen Hawking and Albert Einstein and stuff like that. They were top-notch physicists. So if they can't figure it out, this must be something that's kind of a big deal. Wien did come up with one thing. He came up with what became known as Wien's displacement law, right where that experimentally seen sort of observation suddenly starts to curve downwards. He could predict for you what frequency that happens at, because different stars at different temperatures have that dip in a different spot. Sometimes it happens a bit earlier, sometimes it happens a bit later. And so Wien could predict that. One thing that's noticed is that dip always happens right at around the frequencies of UV radiation. So that's why it became known as the ultraviolet catastrophe. And let's be honest here, when something is a mild inconvenience, you do not refer to it as a catastrophe. This is big deal stuff. But we can also take the other meaning of the word catastrophe, where in physics or engineering, it means a sudden change or a sudden release or a sudden failure of something. So right at about UV, we're seeing that sudden change there. So all these great physicists couldn't figure it out. Somebody's going to have to figure it out. And the person that does that for us is this fellow, Max Planck, because he basically said everybody is assuming things. And granted, we have to do that when we're doing stuff in science. There's certain things that we just believe must be real and true and that we can stick with those. The assumption everybody had been going with was that the electrons that were in a black body object could be vibrating, jiggled around at any frequency. And then when they would release their EMR, it could be at any frequency. Max Planck says, no, maybe that's not true. Maybe there's a minimum energy that's needed to get a particular frequency of EMR, and that those two match together. So it's kind of, think of it this way. I can build a whole bunch of stuff out of Lego blocks, and I can actually make like really big, incredibly complicated structures that look really cool. You just have to go to like a Lego exposition to, see that sort of stuff. But when you get right down to it, when you break it down to pieces, you get these individual pieces of Lego. And once you get down to that point, you can't break it down any further, right? So that's the way he's suggesting to think about these minimum energies, even though they might build to give the illusion of many different energy amounts at different frequencies. Really, it's not. It's individual pieces. It's particular frequencies of EMR that are associated with certain particular minimum energies. He gives a name to this. He calls that individual piece of energy a quantum. And that's where the name quantum mechanics is coming from. It's the study of individual smallest pieces of energy. That's really what all of this chapter is going to be about in some way. Now, the formula he comes up with to be able to calculate this, since particular frequencies have to match up with particular energies, is given on your data sheet as E equals HF. But I do want you to make one little change to that for me, because I think it's going to make your life easier. I want you to think of it as E equals NHF. Now remember, there's a few times in physics where we use the variable n to show like number of something or an index of refraction, something like that. Here, the little n is supposed to represent to us how many quanta, that's the plural form of quantum, how many pieces, how many quanta of that energy we have. You're going to find this helpful when you're doing some calculations, honestly. So E is still energy, typically measured in joules. N is the number of pieces, the number of quanta. And if we just ask you about what's the smallest possible, it'll be for one piece. And if N is 1, it just kind of disappears. H is called Planck's constant. And if you look here and on a data sheet, you'll see it's given as two different values. One of them, 6.63 times 10 to the negative 34 joules seconds. And the other one, 4.14 times 10 to the negative 15 electron volt seconds. I hope you can see the difference there. It's whether we want our energy answer to be in joules or electron volts. And what I tell people is we usually should do our work in joules because it makes it compatible, if you want to think of it that way, with every other formula on the data sheet. Because as soon as we do get into electron volts, yes, sometimes it makes doing some of the questions easier, but it does mean that later we might have to convert our electron volts into joules when we want to use some more classical physics sort of formulas. But it does depend on the question. I would just say usually stick with 6.63 times 10 to the negative 34 joule seconds, unless you've got a good reason to use electron volts. Maybe they're asking for the answer that way. And finally, frequency is the frequency of the EMR itself. So I tell you that I want to know the smallest amount of energy that can be produced by a light source if it emits light at a frequency of 4.50 times 10 to the 14 hertz. So for this one, we are just going straight ahead with the formula E equals HF. I'm not even putting in the N, because if it's the smallest amount of energy, it would be one photon or one quanta of energy at this point. So if N is 1, I don't even have to write it there. E equals HF. I'll go ahead and I'll put in regular Planck's constant. I put in the frequency, and I find out that it comes out as about 2.98 times 10 to the negative 19 joules. If I did it with Planck's constant in electron volts, I would be getting 1.86 electron volts. A number that just looks nicer, but still remember it's going to be something that could potentially cause some issues for us with other formulas. The other caution I'll give you is that if you do a lot of the later section questions involving quantum stuff, if you do it in joules first and then convert to electron volts instead of doing electron volts from the beginning, you might find your answer shifts a bit. Like here it's 1.86, and then you'll do something with a slightly bigger, more complicated problem, and you get 1.84. That's because the numbers that we're using for the conversions are themselves rounded off, obviously, to 3 sigdigs, and it means that there can be these little fluctuations because of the differences in the rounded off values that we're using. But those are taken into account when answer keys are made up for questions so that you can get the right answer your way or the other way, and everything is still fine. You'll see when we get to later sections, later lessons, how that can happen. Now, the other question I'm asking is, what's the minimum energy? So again, only one quanta that can be transferred by a light source at 212 nanometers. And I want this measured in electron volts. Now, two things here. I'm going to use Planck's constant in electron volts, but maybe more importantly, I'm also going to come up with a slightly different formula, because here it's giving me wavelength. Now, I do know that we're dealing with light, so I could use the formula C equals F lambda to change this wavelength into a frequency, because all light travels at the speed of light. Change a wavelength into a frequency and then use the formula that's given here. Or I can take the formula, the universal wave equation with C for light, C equals F lambda, and I could manipulate it for frequency, and then I could substitute it in where frequency is, and I would get E equals HC over lambda. This whole thing is written on your data sheet so that whether you're seeing frequencies or wavelengths in your question, you can just jam the numbers in and start working on your answer. So I'm putting in, because I have an intentional reason, the Planck's constant in electron volts, because the question's asking me to give the answer in electron volts, speed of light, and the wavelength, and I did change the nano to 10 to the negative 9 so that I can get the calculation correct, and I get 5.86 electron volts. Now this is where Albert Einstein comes in, and I'll admit a couple slides back I did a little bit of a flub, and I started to say a word that I shouldn't say until we get to this slide, because I was talking about the quanta of energy. That's all that we've talked about so far. But here's basically Albert Einstein's reasoning. Planck is talking about energy that's coming in pieces. But where's that energy coming from? It's some form of EMR. So if the energy comes in pieces and the energy is coming from some form of EMR, that means the EMR must be in pieces. This is where we get back to that idea of, is light a particle or a wave? Well, it's both. It's a wavicle, wave-particle duality. What we're seeing here is that evidence that light, in this situation, when we're examining its quantum effects and measuring things like blackbody radiation, I need to think of light as being a particle. And the name that he used for that is the one that I started to say a couple of slides back, photons of light. So the energy comes in quantum pieces, and that means that the light must be coming in pieces called photons. So I tell you that we go to the store and we're going to buy a laser, and it says on the package that it runs at a frequency of 4.38 times 10 to the 15 hertz. That in and of itself is a little bit odd, because most often they'll give laser specifics as like a wavelength, for example. But here I gave it to you as a frequency. It also says that it runs at 4.06 MW. Hey, that's milliwatts. That's a measurement of power. And I want to know how many photons, how many particles of light can it release in 1 second. So I'm going to bring out the power formula from back in Physics 20, power equals delta E over T, and I'm also going to bring out our quantum formula, E equals NHF. And here I'm choosing to use the version of the formula that has frequency, because they gave me a frequency. I'm going to use Planck's constant that has joule seconds, because I want everything to be consistent with standard units. And I'm definitely going to keep N in the formula, because the question's actually asking how many pieces. And if I know how many pieces of energy there are, that's also how many photons there are, because each piece of energy is related to 1 photon of light. So I took the formula for power and I manipulated it, solved it for energy. So it's equal to PT. And then I'm going to stick that on to the formula that we have for quantum mechanics, because that energy is the energy that's being changed from the photons of light, and the packets of energy that we're dealing with. So PT equals NHF. I want to solve this for N, so I've got PT over HF. And the thing that I'll stress to you here is this is something else we have to be aware of, we have to be prepared for, is this ability to take formulas, something from Physics 20, and relate it to the ideas that we're talking about now to be able to answer our questions. Everything is becoming interrelated now. I stick in my values. The power is the power that was given to me. It's milliwatts, so 10 to the negative 3. They told me they want to know how many I can release in 1 second, so the time is just 1. Don't be surprised, though, if you were told the laser was kept on for 3 minutes, and then you'd have to say, well, there's 60 seconds in a minute, 3 minutes, that'd be 180 seconds. You got to be prepared for questions like that as well. Or they'll ask you how much time did something run. Anyways, H, putting in regular Planck's constant, because as soon as I started saying I'm going to use the old power formula from Physics 20, I've got to make sure I'm using standard units, and Planck's, I should say the frequency, 4.38 times 10 to the 15 hertz. Putting some brackets around the top, putting some brackets around everything on the bottom to keep order of operations together. I should get 1.40 times 10 to the 15 photons. That's a lot of photons. But this makes sense, because when we do think of light, we have to basically say that when we're observing its particle nature, the particles must be wicked tiny, small things individually. And that's why there's so many that are released in that 1 second that this little laser is turned on. That's it for the beginning part of quantum mechanics. We've still got other stuff that we got to figure out to be able to work everything out, but you can sit on this first little bit here and just kind of think about the implications of it. Have a good day.